Dielectrics and polarization. Dielectrics are certain substances which are used inside a capacitor to insulate the plates. Actually, dielectrics are not merely used to insulate the two plates, but it has got another role in determining the capacitance of a capacitor. So we can see what are dielectrics. Dielectrics are non-conducting polar or non-polar substances. So there are two types of dielectrics, polar and non-polar. So what are polar dielectrics and what are non-polar dielectrics? In an ordinary atom, we know the entire positive charge is concentrated in a small region called the nucleus. So we can imagine that the nucleus is in the shape of a sphere. So the entire positive charge of the nucleus can be assumed to be distributed at its center. And again, the electrons are seen around this nucleus in the form of a negatively charged cloud. And if this electron cloud is uniformly distributed around the nucleus, so if it has a regular shape, you can say spherically distributed, if there is symmetrical distribution, so the entire negative charge also can be assumed to be concentrated at a particular point. So these points we can call the center of charge of the positive charge and the center of charge of the negative charge. In certain materials, these two centers, that means the centers of positive charge and centers of negative charge, will coincide each other. But in certain other materials, the centers of the positive charge and negative charge will not coincide each other. Now that is the basis of the classification as polar and non-polar substances. So see, this is a particular substance. This one is the center of the positive charge and the center of the negative charge is somewhere inside here. So it is very clear that the centers of positive charge and negative charge are separated by a distance, and these type of molecules are called polar molecules, and that substance is called polar substances. So this is an example of a polar substance. So it is very clear in this, the centers of positive and negative charges are not coincide inside a molecule. So this molecule will have an extended shape like this. Now examine this. So this negative charge is symmetrically distributed over a spherical area and the center of positive charge is also marked here, and this centers of both positive charge and the negative charge are coinciding at a particular point. And this is an example of a non-polar molecule. So this is a non-polar molecule, but this one is a polar molecule. So what will happen to a non-polar molecule? If a molecule is not possessing a non-polar molecule, it will not behave like a dipole because the centers of positive and negative charges are not separated. But in the case of a polar molecule, there is a small separation between the centers of positive and negative charge. So this molecule is behaving like a dipole and it possesses a permanent dipole moment. Even though the single molecule is possessing a permanent dipole moment, but due to the random orientation of the molecules in the substance, the substance as a whole will not show any resultant dipole moment. So there is no dipole moments inside a polar molecule, but under ordinary conditions, even though the individual molecules are possessing dipole moment, the net dipole moment of a non-polar substance also is 0. Now what will happen if a non-polar substance is placed inside an external electric field? If a non-polar substance this is a non-polar substance. If a non-polar substance is kept in an external electric field like this, you can observe these two figures. In the first figure, electric field is 0. The external electric field is 0. But the second figure, the external electric field is not 0. It is acting in this direction, from negative to the positive x direction. So these molecules are not possessing any per dipole moment because the centers of positive and negative charges coincide. But under an external electric field, you can see because of the force acting on the centers of negative and positive charges, the negative charge center slightly displaces in a direction opposite to the electric field, so that this molecule extends itself. So now this molecule is possessing a dipole moment. So even though a dielectric is non-polar, when you apply an external electric field, these molecules will behave or will become polar and they will possess a dipole moment. So this is what is happening when a non-polar substance is kept in an external electric field. Now let us see what happens with a polar substance when it is kept in an external electric field. So these two figures. So this is a this is a polar molecule. This is a polar substance kept in the absence of an external electric field. This figure at the same time shows a polar substance kept in an external electric field. The external electric field is acting in this direction as the arrow indicates. So you can see one thing. What is the difference? In this case, the polar molecules are randomly distributed so that their total momentum is 0. But you can see that all these polar molecules will arrange in a particular order, so that this is possessing a dipole moment. So this is the major difference between the behavior of a polar molecule and a non-polar molecule in an external electric field. A non-polar substance becomes polar, and a polar substance, all the individual molecules will be arranged in a particular order. The electric field inside a dielectric in an external electric field. Now let us check what will happen if you keep a dielectric substance in an external electric field. So if you keep both polar and non-polar substances in an external electric field, another electric field is created inside it due to the polarization. So this figure explains it. So this is the dielectric substance, and an electric field is applied here, which is denoted by E0, acting in the positive X direction. So the molecules are having a separation of charge centers, so they have a dipole moment. So at this end we have free positive charges located here. At the same time we have negative charges located at the other end. So this end of this dielectric slab will be at a positive potential, and this end of the dielectric slab will be at a negative potential. So because of this positive and negative charges, another electric field is set up inside the dielectric, which is denoted as EP, the electric field formed due to polarization. And this electric field will be opposite to the direction of the applied electric field. So now there are two electric fields inside a dielectric. One, the external electric field is 0 in one direction, and the second one, the electric field produced due to polarization, that is in the opposite direction. So the resultant electric field inside this slab will be E, that's equal to E0 minus EP. So whatever may be the case, whether it is a polar molecule or a non-polar substance, the resultant electric field will be less inside it when we keep that one in an external electric field. And the total electric field is given by E is equal to E0 minus EP. And it is found that the ratio of E0 to E is a constant for a particular substance, and this ratio is called the dielectric constant. So the dielectric constant is a ratio of the applied electric field to the resultant electric field inside the dielectric. So what will happen if you keep a dielectric slab in the region between the two plates of a capacitor? The effect of dielectric in a capacitor. When a dielectric slab is placed in between the plates of a parallel plate capacitor, Due to the polarization of it, the electric field and hence the potential difference between the plates decreases. A decrease in the potential difference causes an increase in the capacitance. Now let us consider a parallel plate capacitor. Let A be the area of each plates and separation between them is D. If the space between the plates is air, its capacitance is given by C0 is equal to epsilon 0 A by D. The capacitance depends upon the area of the plates and the distance between the plates. The electric field in the region between the two plates of the capacitor is E0 and the potential difference across them is V. And this E0 and V are related as V0 is equal to E0 into D. And the charge on each plates are given by Q is equal to sigma into A, where sigma is the surface density of charge. This is the same capacitor. Now I am going to introduce a dielectric in between the plates of this capacitor. So this is the plate A and this one is named as B. A is positively charged and B is negatively charged. And D is the separation between them. The electric field between the plates is E0 and it is acting in the positive X direction. Now we are introducing a dielectric slab in between the plates. Thickness of this dielectric slab is T. So, due to the polarization of the dielectric, an electric field is created inside this dielectric, but it is directed opposite to the existing electric field E0. So, two electric fields are there inside this dielectric. So, the resultant electric field will be E and that is equal to E0 minus EP. The resultant electric field in the slab is given by E is equal to E0 minus EP. E0 is the electric field in between the plates of the capacitor and EP is the electric field produced due to polarization. And we know that this E is equal to E0 divided by K, where K is the dielectric constant of this particular slab. The potential difference between the plates is defined as the work done to bring a unit positive charge from this plate to this plate. But in this situation, we are not moving through the same electric field. From B to the end of this dielectric slab, the electric field is E, which is equal to E0 by K. After that, the electric field is E0. So to calculate the potential difference between the plates, I am going to find the potential difference between these 2 points and then the potential difference between these 2 points. So if I will add these two potentials, I will get the total potential difference between B and A. So the potential difference across B and the end of this dielectric is E into T, because E is the electric field and T is the this much distance. And after that, the work done to move the charge from here to here is E0 into D minus T. The remaining distance is D minus T and the electric field acting there is E0. Now we are able to calculate the capacitance of this capacitor. Capacitance is given by the ratio of charge to the potential difference. The charge is given by sigma into A and the potential difference is given by V is equal to E into T plus E0 into D minus T. Substituting the values of Q and V, we will get this expression. Then this E can be written as E0 by K. Therefore, the C will become sigma A divided by E0 by K into T plus E0 into D minus T. It can be further simplified as sigma into A divided by E0 into T by K plus D minus T. Again, we can make a substitution here. E0 is sigma divided by epsilon 0. With that substitution, the C becomes epsilon 0 into A divided by T by K plus D minus T. Now, What will happen if I fill the entire region inside this capacitor with the dielectric? In this situation, the thickness of the dielectric slab becomes equal to the separation between the plates. If the capacitance, the new capacitance C is given by C is equal to epsilon 0 A divided by T by K plus D minus T. Now we can apply our condition here, that is T is equal to D. The thickness of the slab equal to the spacing between the plates. So C is equal to epsilon 0 A divided by D by K plus D minus D. D minus D is 0, and finally the capacitance. The new capacitance is given by K into epsilon 0 A divided by D, and that is equal to K into C0. Therefore, by introducing a dielectric slab in between the plates whose thickness is equal to the spacing between the plates, the capacitance of the capacitor becomes K times. What is K? The dielectric constant. So, if you can select a material of high dielectric constant, we can increase the capacitance without changing its dimensions. So this is the best way of increasing the capacitance of a parallel plate capacitor.